Hi, everyone. Hi. Netflix uses more than 4,000 servers on their cloud on their AWS to run Kafka, and they run it to transport over 700 billion events every day between the microservices and to monitor the microservices. This is very impressive. They have one of the biggest architecture running Kafka at scale. In this talk, we'll see how Kafka works from the scale of the OS kernel to the scale of worldwide clusters. My name is Flavian. I'm a data scientist at Sikara. And Sikara does projects in data science and data engineering for their clients. We have, among our clients, you find EDF, Société Générale, and Renault. I've used Kafka on a project for Content Square. Content Square, I don't know, who knows Content Square here? It's a startup company. They build a product to help the clients analyze the UX of the website. It's basically Google Analytics for big companies. They wanted us to build for them a session replay tool. A session replay tool is a tool for the clients to be able to replay the end users' sessions for the admins. This meant for us that we needed to record and store on AWS all the events from mouse events, mouse clicks, document object model mutations, raw HTML pictures, etc. And everything was being transported in Kafka. So this was the plan for this talk. First, we're going to see what is Kafka, then who uses Kafka, who builds Kafka, how does it work. So I said from the OS kernel to the worldwide clusters. And in this section, we also see the case of Content Square. When should you use Kafka? When should you not use Kafka? And finally, hopefully, I get a round of applause from your part. So first, what is Kafka? Does anyone here know what is Kafka? Anyone? No? Yeah, a little bit? Okay, can you define it very, very quickly? A bus and a database. Yeah, that's pretty good. So Kafka is a distributed, replicated, fast, and reliable immutable log of events. It's distributed because the immutable log lives on multiple servers across your cloud engine. It's replicated because all the data is replicated between the servers. It's fast. It's actually one of the fastest when used as a message queue. And it's very reliable because once a message, an event is in Kafka, it stays in Kafka. But then who uses Kafka? I've talked about the case of Content Square. I've talked about Netflix. Among the users of Kafka, you'll also find Twitter and Airbnb. Also, the New York Times, they store all the articles and all the revisions for the articles in the immutable log, that is Kafka, and they can replay all the events from the start of the 19th century to now, and they have that at scale. Who builds Kafka? Kafka was created originally by these three people. So there's Nihan Arkid, and I forgot the names of the other ones, but you can look it up. It was created at LinkedIn. Then it was made a part of the Apache Foundation in 2012. And finally, they created Confluent in 2014 to build and maintain tools around the ecosystem. Then how does Kafka work? Let's start at the micro level, and let's remake Kafka in 5 seconds from scratch. So here I've got an echo command that I'm writing to a file. And on the right side, I can tail this file. And this is basically what happens in Kafka. On the left, you have a producer of messages. On the right, you have a consumer. This is really how it happens in Kafka, and the files are what will be called partitions. So Kafka is very fast. Why is it fast? Because it writes everything to disk. It's fast because it uses linear writes on the disk. Every event is written on a sequential fashion on the disk, which means that you can write very fast. You can write faster than on the random writes on RAM, which means that it's also why it's faster than traditional message queues like RabbitMQ. Why is it reliable? It's reliable because everything is written directly on disk. They use zero copy from the OS functions, which means that from the network socket to the disk, there's a one-way path, and it never goes in RAM. Contrary to RabbitMQ, which will write all messages in RAM and then sometimes flush to the disk, which means that if the server breaks down, you don't lose data. So now let's go at the server scale. This is how an event is made. An event has a key, it has a timestamp, it has binary content, it has some more stuff like a magic number and things like that, and the Kafka version. The key is used to identify uniquely a message, an event. The timestamp, well, you know what it is. And the binary content can be anything from raw UTF-8 strings, JSON, Avro, and things like that. It's also, the compression is in the events in the binary content. All the events are contained in topics, and the events are produced and consumed by external processes. Kafka is actually a dumb broker, only it doesn't care really about who produces and consumes messages. The topics are partitioned, and the partitions are files on the disk, just like we saw earlier. You've got a producer here that writes data to new partitions, and there's a number, an offset that is kept track of the number of messages in each partition. If you care a lot about disk space, you can set up retention on the partitions. This means that you can say, OK, I want to keep all the messages that are at most 2 weeks old, and then get rid of the rest. If you care a lot about keeping the rest of the files, and you care a lot also about your disk size, you can use log compaction. So here on this example, the shapes are unique keys, and the values are colors. So here you've got, for example, 3 square keys. And if you use log compaction, it will keep only the newest key. So for this set of events, it keeps only the newest ones. This allows you to keep the freshest event from the start of your history. Topics, they preserve the order of events, but only within a single partition. They're also replayable. If you have a consumer, you can say, OK, I want to start from the beginning of the topic, or I can only tail the latest messages. So let's see another example. We will use KafkaCat. KafkaCat is both a producer and a consumer of events. And we will use the tool which is included in Kafka, which is called dump log segment, to have a look at the inside of a partition. Here I started Kafka with the Confluent binary tool that you can find on their website. It allows you to start very quickly Zookeeper and Kafka servers locally. And on the top right and top left, I've set up a producer and a consumer with KafkaCat. So here I'm writing messages. I write hello, Web2day. And on the bottom right, you can see that there's an offset. Here I'm going to have a look at the actual files on the disk. So I'll ls a special directory here in Kafka data and the topic that I want to read. There's a file called .log, which if we read it, it's only binary content that you can really understand, but we can see that the messages that we produced to this partition are on the disk, and they are readable. If we want to read them completely, we use dump log segment, and In a few seconds, it's gonna show. Okay, here you have a payload Web2day. You have the offsets and different information metadata for the events. This allows you to debug very efficiently if there's a problem on Kafka, because you can actually have a look at what's inside. Now let's focus on the producers and consumers, which are side applications from the broker. A producer produces events to partitions, produces them, so it defines the key of an event, and also defines which partition the key is assigned to. By default, the keys are going to be random, and the partitions they're going to be sent to are going to be random as well, but you can make a deliberate choice to send all your events inside the same partition. This is, for example, what the New York Times does. They have only one partition for all the articles. About producer reliability, you've got several levels, which are trade-offs between speed and reliability. First, you can just send and forget events. I send events, and then I don't care if they arrive or not. I don't care about that. But if I do care about if they arrive, I want to do synchronous sends, which allows you to restart sending an event if the broker says, OK, I never got it, or if the event times out. Synchronous sends, they will block the execution of the code until your event is actually acknowledged by the broker. The in-between between those two are asynchronous sends. You send events, and you can restart sending them if there's an issue. The catch here is that you can lose order of events. For example, if I send the first message, it doesn't arrive to the broker. I send the second message, this one arrives. The first message is going to be retried, but the second has already arrived. So you've switched the order. On the consumer side, consumers are assigned partitions when they start. The process that is being done in a consumer, first it pulls data from the broker. It sends a special request to get data from the broker. Then it does some processing, so that's code that you actually need to write. And finally, it commits offsets. The offsets are the way of the consumer to say to the Kafka broker, OK, I'm here in the log. And the broker remembers that and knows which consumer is where in the partition. It's only an integer, so it doesn't have a high footprint for Kafka. And it's also written on disk, this offset. So this is the anatomy of a topic. And there's also, for each consumer and each partition, where the consumer is at in the log. So these are the offsets I was talking about. For example, consumer B for partition 0 is at the offset 4. Consumer A for partition 1 is at offset 7, etc. If you want to scale the consumers, you define a consumer group that is going to consume all events and share the load for all events in a cluster. You can have several consumer groups to consume from a topic. And for example, if this consumer, which has been assigned these partitions, so it means that the other partitions are assigned to the other consumers. For this consumer, if it keeps missing messages, then it's considered as dead, and there's going to be a process called repartitioning, where the partitions from this consumer are going to be allocated to the other consumers, which allows the consumers to keep running and keep processing events. So as an interlude, let's talk about the case of Content Square. Content Square, the goal is to store 1 billion events, which is about 7 terabytes a day, on Amazon S3. All these events come from the browsers of the end users. For example, here you will have 2 files for one user. The first is for page 0. The second is for page 1. They wanted to keep separate the files for each page and each user. Also, we want to minimize the number of requests on S3. Why do we want to do that? It's because because of the cost. On S3, you pay for all the network operations, and that's basically it. You don't really pay for storage space. Well, actually, it's very minor. So we want to minimize the number of requests, CRUD requests, that are done on S3. The global architecture is this one. You have a web browser which is connected to a web server which is going to produce events in Kafka, and then those events are going to be consumed by consumers, grouped together, and sent as files on S3. As an example, first we have an event that is click from Joe on page number 1. This event is assigned a key that is unique to the couple Joe and page number. Here the key is AE6271. The second event has the same user ID and page number, so it's going to be sent in the same partition. And then the third event is also a click, but it's on another page, so it's going to be sent in another partition. We have 1,000 partitions in our Kafka clusters for Content Square, and this allows us to have a lot of consumers to gather data at the end. For Content Square, we also wanted to limit the number of polls so that a consumer processes. You want to maximize the chance that a consumer produces a whole session, user session. So we had a lot of consumers, and they were waiting to have at least 10 megabytes, which is equivalent to 2 sessions, to start processing. This means that sometimes the consumer was idle. We was waiting for enough data so that we could do only one post request, one file creation at the end. We also set a maximum time for the consumer to wait for data from the broker, which was 5 minutes. This allows us to, for example, if it's nighttime and you don't have a lot of users on your application, you don't want you still want your events to be processed at some point. Okay, you can use those 3 configuration options to do that. The processing part is we grouped messages by key and inserted them in the same S3 file. This is actually a bit harder than that, because you need, if you have already written a file for one user and one page number, you have to fetch this file, merge the new events with this file together, and then repush this. At the end, you have files on S3, and finally, you can take a file and pull it into the replay session to replay all the events, all the DOM mutations, and so on. So we completed the circle. So now let's have a look at the scale of a cluster of Kafka brokers, and let's see what happens. Here we have 3 brokers in one cluster. So at the start, Zookeeper, which is the configuration server that is used to handle configuration for Kafka, is going to assign one ID to each broker, which is unique. So here we have 1, 2, 3. And at the start, Kafka elects one broker as the main broker, which is going to then elect leaders for partitions. Why do they elect leaders? It's because when you create a topic, it creates a file on disk. You create multiple files on disk, actually, so which are one for each partition. And a leader is going to be the primary broker on which this file is going to be stored. All the data that is produced by a producer is going to be produced to the leader that contains the partition the events are sent to. And for example, here you've got a producer for topic B, it's blue, and it's going to produce messages only to brokers 1 and 3, which are leaders for the topic B partitions. For consumers, there are assigned partitions, so they only need to consume data from the broker that have their partitions. So here you have two consumers that consume one from broker 3, the other from broker 2. If one of the consumer in the consumer group dies down, the consumer is going to consume from all the leaders which have the partitions. How do you make this system reliable? You make it reliable by adding replication. For example, here we zoom on partition 1. We decided that it had one replica, and the leader for partition 1 is broker 2. The leader is going to decide that one of the brokers in the cluster is going to be a follower for partition 2, and it's going to act. The broker 3 is going to be the follower, and the 3 is going to act as a consumer for partition 1. So it's going to fetch the latest data from broker 2. This means that if broker 2 dies down, then broker 3 takes its place. And it's elected as a new leader. It's called leader election in Kafka. All the consumers and all the producers are notified so that they can produce and consume messages only from 3. So this means that for some time, there's going to be, you won't be able to produce or consume data, but since you have an internal buffer in the producers, it's OK. Another thing for reliability here is that sometimes broker 3 will have less data than there was in broker 2. And I've said at the beginning that you never lose data. Why do you never lose data in this case? It's because when you produce an event, you can set a configuration option to get an acknowledgement only if the message has been received and replicated to the other brokers. So this way, you only produce and consume data that you can produce and consume data that has already been replicated. You can find more about replication here. I've left a link, and I will tweet the slides after the talk. So now let's get worldwide and see what happens at the worldwide scale. Here you have 2 regions in Amazon. For each region, you have 2 availability zones, and in each availability zone, you have 1 cluster for Kafka. We're going to use a tool called Mirror Maker, which is both a producer and a consumer of events. It's going to consume events from one broker and consume it to another broker, which can be in different clusters. The first pattern you can use is to use one central cluster for reports. This is if you only care about your data being available locally. Here you have 3 local clusters that can deliver events for local apps, and you have 1 central cluster for dashboarding, monitoring, and things like that. You have the active standby architecture, which doesn't allow you to replicate data between regions, but it allows you to replicate data between 2 brokers and use one as your primary broker in prod and the other as a backup. It means that if you have a DNS server that allows you to point to one broker and the other, you can, if one of the clusters, is down, you can very quickly switch to the other with fresh data. Finally, you have active-active replication. This allows you to replicate data in 2 ways between clusters. This is actually a bit dangerous because if you have an event and you send it to another cluster, then it could come back if you are not careful. So you will have an event that is replicated back and forth, and then it clogs your disk, and it's not a good thing. To avoid this, you can use metadata to say, OK, this event was already mirrored to another cluster, and it's never coming back. You have also stretch clusters. Stretch clusters are regular clusters of Kafka, but they are stretched across availability zone, which you can do because in AWS, you have availability zones which have low lag and high bandwidth between them. This means that you can have different brokers in different availability zones. They are called stretch clusters because there's a special configuration to say, OK, this broker is on this rack or this data center. And also, you can use active-active replication between those stretch clusters to synchronize data globally. When should you use Kafka? From these examples, you should use Kafka when you have high volume of data and you want to use Kafka as a buffer between the producers and consumers to avoid any data loss if your consumers are not fast enough. You can also use Kafka to decouple microservices in a microservice architecture, because as you may know, the main cause of failure in a microservice architecture is that if you have one service which depends on another service, which depends on the third service, if the last one breaks down, all the other ones break down as well if you're not careful enough. And Kafka allows you to be your communication layer between all these microservices. Finally, if you work in a large organization, you may have a data lake, and it's useful to have Kafka in your data lake because you can have different teams which are decoupled, which are going to consume data from Kafka, and they won't have any dependency on one another. When should you not use Kafka? You should not use Kafka if you need all your messages to be ordered. So this means that in Kafka, the ordering is up to the size of your lowest capacity disk. If you need all your messages to be ordered, you should use another, like all the messages, if you have more than 1 terabyte of messages, you should use another technology. If you need very tight security and fine-grained ACLs, you should not use Kafka as well. Security in Kafka is fairly new. They have authorities, they have authentication, they have things like that, like OAuth that is coming in the next version. You have also ACLs on the user level, but for example, you can have at the moment group authorizations in Kafka. I've left a few things out. So I've left the topics here so that you can have a look at the slides later. And I've left also a group of references here for you to read. They are all very interesting. There are books, articles, and videos. And with this, let me thank you. I will send the slides on my Twitter later. Thanks.